Hello, and welcome back to the next lecture in this series about the Church-Turing thesis. Why are we talking about the Church-Turing thesis? What is it? Why are we talking about Turing machines at all? Well, we have Alan Turing to thank for that. But why was Turing motivated to build these machines, this mathematical model? And what did Church do? They were working before we had electronic computers and long time before anybody was building programming languages that look anything like modern programming languages. So why were they motivated to essentially build programming languages? Let's try to set the stage for what they did by saying a little bit about the historical context. So David Hilbert was a famous mathematician in the early 20th century and before. And not only was he a famous mathematician, but he was also famous for being a famous mathematician. And when he suggested, here's a problem you might want to think about working on, well, a lot of people would sort of stop what they were doing and would work on that problem. And in a very influential lecture at the dawn of the 20th century, Hilbert set out a long list of problems, one of which was to find an algorithm for solving Diaphantine equations. If you don't know what a Diaphantine equation is, be patient, I will let you know. And then a while later, he posed another question, very algorithmic in nature. Find an algorithm to decide, given as input a first order logic statement, to figure out if it's valid. And there are variants on this to try to figure out if a formula or if a logic statement is true, let's say, for the natural numbers. So these are the questions that largely motivated the work of Church and Turing. And why don't I let you know a little bit more about these problems. This first one about solving Diaphantine equations is often known as Hilbert's 10th problem. And this problem about finding an algorithm is, since Hilbert was German, is called the Entscheidungsproblem, which just means the decision problem. It's an algorithm to decide. So there's a very close connection between these problems, actually. And Hilbert apparently never even contemplated the possibility that these algorithms would not exist. But Church and Turing were largely motivated by trying to show that, in fact, there cannot be an algorithm. And in order to do this, a major stumbling block was the fact that nobody had come up with a formal definition of what an algorithm is. I mean, mathematicians have been building algorithms for centuries, if not longer, but, you know, they just knew an algorithm when they saw one. Nobody had ever tried to say, well, these are the only things that can be algorithms, and to try to even start formalizing what it might mean for there not to be an algorithm. And it's worth considering some of the intellectual obstacles that needed to be cleared before they could even do that. But first, let me remind you, or let me make good on a promise about what I need to tell you what a Diaphantine equation is. Let's start this with a simple example. Do there exist integers x, y, and z such that x cubed plus y cubed plus z cubed is equal to 33? The answer turns out to be yes, but this was not known until 2019. And in fact, the X, Y, and Z that have been found are huge. Let's say that the answer was no. Would there be a proof that the answer was no? In other words, could there be a proof of the statement for all X, for all Y, for all Z, X cubed plus Y cubed plus Z cubed is not equal to 33? Well, of course, since they do exist, there can't be a proof of that. But let's say that you had some other number, like 1098. Maybe X, Y, and Z exist. Maybe they don't. A Diaphantine equation, these are actually very simple examples of Diaphantine equations. They're just multivariate equations over with integer coefficients. So, if you have X, Y, and Z, then we might also have some terms, maybe plus X squared Y, or plus Y to the 90th, Z to the 10th. You can have all kinds of terms, just anything you can write down that looks like a polynomial with integer coefficients. So maybe to make sure what we're talking about with integer coefficients, maybe we'll also allow 57 X Z cubed. Okay. That's what a Diaphantine equation is. And much later than the work of Church and Turing, it was discovered, or it was proven after building on a lot of intuition that people had, that in fact there is not an algorithm for this, at least not if there's, let's say, 20 variables. And that also means that there are statements that look sort of like this, except with 20 variables, such that it's a true statement, but there will never be a proof of that statement. In other words, what's the connection between an algorithm to decide if a statement is valid, or it's easier to see about seeing if there's an algorithm to find out if there's a proof of a particular statement. If we're talking about a proof of something being true for the natural numbers, if there do exist X, Y, and Z, then there is a simple proof. You just give the numbers and do the arithmetic and see, yep, it comes out to just what it's supposed to be. And if there is not a solution, but there's a proof that there's not a solution, well, then here is an algorithm that could decide things. Just in parallel, you start trying all short tuples of variables and also the short proofs, seeing if you find a short proof of the fact that there is not a solution. And if you don't have any luck, then you start looking at longer proofs and longer solutions. And if everything that were true were provable, then since there either is a solution or there's not, you'd either find a solution or you'd find a proof that there's not, and that would give you an algorithm. And so the very fact that there is no algorithm for solving Diaphantine equations, which is a complicated thing to prove, and we will not be proving it, but the fact that there is no such algorithm also means that there are some true statements saying that some Diaphantine equation has no solution, but for which there will never be actually a proof of that. And that, of course, depends on what formal system you're using, but no matter what formal system you're using, if it looks like a reasonable notion of proof, then there will be unprovable true statements there. Interestingly, even if there's just a single variable, there is an algorithm for solving univariate Diaphantine equations. It's wide open, apparently, if this is solvable when there are just two variables. So that's the historical context, some of the motivation for why it was interesting to people like Church and Turing to show that there was no algorithm. And I promised you that I'd tell you something about the intellectual obstacles that stood in the way of trying to formalize what an algorithm ought to be. Because intuitively, people knew what it ought to be. It ought to be something that's clear and unambiguous. It should give you an answer after a finite number of steps. And it better be something that you can write down, can be written down. But these three desiderata cause some problems, because if something can be written down, what does that mean? That means it's basically a bit string. And what is a bit string? But basically, it's an element of the natural numbers. You can represent numbers by bit strings, and any bit string can be interpreted as a number. So why is that an issue? Well, consider the following thing that looks like it ought to be an algorithm. On input I, which is just a natural number, but equivalently a bit string, interpret I as an algorithm and run I on some input. Well, let's just use the bit string I itself as an input. Why not? It's there, it's handy for us to use. And then after a finite number of steps, according to this rule, it should give us an answer. And if I of I is equal to 1, then output 0, else output 1. So this certainly looks like it ought to be an algorithm. It's clear and unambiguous, at least if your instructions are clear and unambiguous, then you ought to be able to take instructions and see if they are in fact instructions, and if they are, then follow them. And well, what's the problem? Well, this algorithm, if it outputs 1, outputs 0, so that's a contradiction. It can't possibly do that. But then if it doesn't output 0, then it outputs 1. You know, you're just stuck. So is this an algorithm? It can't be in your class of algorithms if you define something formally, because of this contradictory behavior. So that seems to sort of indicate that you can never really have a very satisfactory notion of a class of algorithms. And what Church and Turing essentially independently hit on was the infinite loop. Not because any of them were really interested in infinite loops, but because they had different approaches to modeling what seemed like computation to them, and what they came up with allowed certainly the possibility of infinite loops. So in other words, they threw out what seems like a pretty important idea that you'd want an algorithm to do, which is to give you an answer after a finite number of steps. And in fact, this is one reason why, in order to define what's decidable, we're really stuck using formalisms that give us infinite loops. That's why we talk about things like the Turing acceptable or RE sets, because if you stick with some computation notion that forces you to always halt, then you're going to leave out some things that are intuitively computable. So what kind of notions did Church and Turing hit on? Church essentially invented the lambda calculus. We're not going to be talking about lambda calculus, although certainly there are lots of places you can go to study about them. Turing hit on the Turing machine, which was motivated by just trying to see what somebody could do, a mathematician could do, if he was given clear instructions and a lot of paper and a really big desk and a lot of time. And fortunately for them, it turns out that, fortunately for all of us actually, it turns out that something is computable in lambda calculus if and only if it's computable by a Turing machine. And by computable, of course, here I really mean acceptable. The languages that are Turing acceptable are exactly the same class of languages that arise when you're studying Turing machines or when you're studying lambda calculus, or frankly, if you're studying any other model of computation like Java programs or C++ or anything else that you're likely to see as a programming language. And so this came to be known as the Church-Turing thesis, which is the belief that if you've got something that intuitively is computable, then you can write a program for it. And nobody who's inventing a new programming language, I believe, really thinks, okay, here's something that we can do with this programming language that was completely impossible before. Maybe they think it's more convenient in the new language, but nobody is really thinking that you can do something wildly new. And that's because they subscribe to the Church-Turing thesis. Now, why is this a thesis and not a theorem? It's because by definition, it can never be proved. It could only be disproved. If somebody comes along with a plausible notion of how something can be computed in the real world, which would allow us to do things that are not computable on Turing machines, well, then we will know that this was just a flawed belief. And there are people who come up with notions, ideas about taking a program and or a machine and bringing it extremely close to a black hole and hoping for certain nice effects from time dilation. And I think that these are never going to work. They need a huge amount of resources, and I just don't think the universe is going to allow something like that. I'm very skeptical about anything that involves infinity. Also, there are people who will claim, let me just highlight that this is controversial. People who take it as axiomatic that the human brain can, for instance, recognize that there are statements that are true that can have no proof. So certainly this takes us beyond the realm of what can be done with mechanical computers. And I find this extremely unconvincing. So if you take it as axiomatic that the human brain goes beyond the limits of computation on ordinary computers and programs, well, then it's an axiom. Of course you can believe it, but I see no evidence for it. And I see, in fact, a lot of evidence that the human brain is actually a pretty limited computer in many ways. So just to highlight the fact that this is not a theorem, we are, as a community, open to the idea that it can be disproved, but it's been around for a long time and it seems pretty well established. And even if somebody does come along with a convincing argument that says that you can do things that are not computable on Turing machines, well, this is still going to be a pretty important model of computation, things that you can do on ordinary computers with ordinary programs. And so it would still be well worth studying. There was something else I thought about mentioning, but let's move on. So we've got a notion of computation that is one that's served us well for well over half a century. Back when I was in grad school, which was less than half a century ago, it was also widely believed that things that you can do with ordinary computers also captured what you could do in a feasible amount of time. Now, with the advent of things like quantum computing, this is even more controversial, although it still arguably hasn't been demonstrated that quantum computers can do anything that involves yes/no questions that they can do significantly faster than deterministic machines, although certainly there's some evidence that maybe that should be true. We're not going to be getting into that, and certainly not in my lectures, and I don't think anywhere in this course, but it's just an example of how the assumptions that underlie our mathematics are open to change, and if some new models of computation come along, we are well equipped to study them, and we will do so. But in the meantime, there are a lot of reasons to be interested in what you can do with ordinary computers. And especially the focus of this series of lectures, what can't be done. So next time, we will be giving some examples of problems that are undecidable. So until next time, bye-bye. Hello, and welcome to the third and final installment in this series of lectures, where we're going to introduce a few undecidable problems. So what did we do in the last lecture? We mentioned the Church-Turing thesis, and it occurs to me I didn't actually give you one of the punchlines. Namely, Church and Turing each did succeed in answering Hilbert's Entscheidungsproblem. In other words, they showed that there will never be an algorithm to take as input a formula in first order logic and say, is this a valid formula or not? On the other hand, that set, the set of valid formulae, is recursively enumerable. It is Turing acceptable. Why is that? Because there is an enumeration of all of the theorems. It turns out to be the case that anything that's valid has a proof, and you can just enumerate proofs, enumerate all the one-letter proofs, all the two-letter proofs, all the three-letter proofs, and each time you find a proof of a theorem, you can enumerate the thing that was proved, and so that shows that the set of valid things is enumerable. What Church and Turing showed was that it is undecidable. Let's give some other examples of undecidable problems. And in order to motivate that, the first thing we're going to do is talk about an important notion called the Universal Turing machine. So what goes on with the Universal Turing machine? What makes it universal? Well, remember, we made the argument that no matter what programming language you're working in, anything you can do in that programming language, you can also do with a Turing machine. And it's certainly the case that in any programming language, you can write a simulator. What is that? It's a program, here I'm calling it sim, that takes as input the encoding of a program and some string X, and you run the program on X. So I'm using these angled brackets the same way that the textbook does to indicate that the bit string that represents a program is this P with angled brackets about it, and that's differs only in a very slight way from the program itself or the function computed by that program. But it's it's a difference that's being highlighted in the notation that way. So since if you can do that in your favorite programming language, well, then you can also do it with Turing machines. And that machine is called the Universal Turing machine. What does it do? It takes as input an encoding of a machine M and a string X, and it outputs whatever M outputs on input X if that computation halts. And otherwise, we just say it's undefined, which you can think of as meaning the computation doesn't halt. Now, this machine, like any other machine, has some language that it accepts. And we call that the language of that machine, L of U. And that has a very special name. We call it A sub Tm, which is those pairs M of X, M and X, such that W is accepted by machine M. Okay, so A sub Tm is certainly going to be one of the languages that we'll be working with. And the very fact that there is a simulator is certainly a crucial and important fact about Turing machines. Now let's move on to the question about what are some examples of things that are undecidable. The first thing that we should note before we give any specific examples is that there are only countably many programs because what is a program? A program is just something you can write down. So it's an element of sigma star, and sigma star is a countable set. And so this is also certainly true for Turing machines. There are only countably many Turing machines, but there are uncountably many subsets of the natural numbers or of 0, 1 star. In other words, there are uncountably many languages. So in some sense, hardly anything is computable. There are just way more languages, way more functions than there are programs. So hardly anything is computable, but that's not nearly so interesting as to know some specific examples. And one famous example, one important example to know about is the halting problem. There are different versions of the halting problem. We're going to define it as being the set of all machines M and input X, such that M on input X halts. Different texts would define this as being the set of all those machines M that halt on their own input, on their own encoding. And I don't want people to freak out when they always encounter these examples about programs being run on their own code, because this is something that happens all the time. There are a lot of programs that take other programs as input. Think about compilers, for example. If you've got a Java compiler, you can write that in Java, and you can use that compiler on its own code to compile its code. So there's nothing really weird about having programs run on their own input. It happens all the time. And we will certainly be seeing other examples, which maybe do look a little bit weird later in this lecture. So I will claim that the halting problem, let's just call it H, is recursively enumerable. It's Turing acceptable. Why is that? Well, you take as input M and X, you run using our Universal Turing machine, you run M on input X, and if that computation ever halts, then you go to an accepting state, and otherwise, of course, if it doesn't halt, there's nothing to worry about. You will never halt, and in particular, you will never accept. So it's definitely Turing acceptable, but it's not decidable, which means that H complement is co-RE and not RE. Okay, so almost all of the examples that we will be giving, well, in fact, every example that we'll be giving in this lecture is going to be something that is computably enumerable and not decidable. Therefore, its complement is co-RE and not CE. Okay, so how do we prove this? This is a theorem. It'll be a proof by contradiction. Assume otherwise. So in particular, assume that halt is some subroutine, some program that decides H. Well, then consider the following program, which I'm going to call bad. Bad takes input the encoding of a machine, M, and what does it do? It runs program halt. So if halt, that subroutine, that magic subroutine on input M, comma, M says yes, then this program will loop forever. And otherwise, it will halt. And let's say halt and accept, whatever. Okay, so this is a program. And like any program, it can be represented by a bit string. And I'm going to call this bit string B, the encoding for that program B. So the question now is, does program B halt when it's given its own code as input? Remember, it's a program. You can run it on any kind of input, including its own program. And I'm using this down arrow to indicate halt. So this is the question. And note that if the answer were yes, well, then what's this program do? It goes, remember, we're running B, which is this program, on its own code. And if it does halt, its program by definition is going to output yes, which means that this program B will loop forever, which means that if the answer is yes, then the answer is no. So that's impossible. So that means that the answer is no, but if the answer is no, you go down to the otherwise or the else part of this statement and you halt. So if the answer is no, then the answer is yes. That's a contradiction. So in other words, this program is nonsense. It can't possibly exist, but it does exist assuming that halt is a routine. In other words, if there's a Turing machine, if there is some decidable algorithm that halts and actually decides the language H. So that means it's not decidable. So good enough. What's something else that we can now say is not decidable? Let's look at A sub Tm. We're going to claim that this is recursively enumerable, computably enumerable, and not decidable, which means that its complement, A sub Tm, is co-RE and not RE. So we're going to assume that A sub Tm let's call it accept, is some subroutine that decides A sub Tm. Now, what does that program look like? Again, we're going to call it bad on input M if, now we're going to call accept on this input MM is yes, then we will reject, we halt and reject. Else we will accept. So if I'm given a subroutine that always halts and returns yes or no, then this routine bad is certainly something that we can write. And now let's call this piece of code B. And the question is now, is the encoding of B in the language accepted by that machine B? Well, what do you think? If it is, then our subroutine AX is going to say, yes, this program that we're looking at, B, accepts if we run it on input B, and in that case we reject. So if it is accepted, it's rejected, so that can't happen. Therefore, the only possibility is that it's not accepted, which means that this is going to return no, which means we go down here to the otherwise, and we accept. So if it's not accepted, then it's accepted. Again, we get exactly the same contradiction. So there you have it. Yet another example of something that is Turing acceptable and not decidable. So remember this handy dandy diagram where we have the computably enumerable sets and the co-computably enumerable sets. We've shown that the halting problem and A sub T M, and actually also, don't have room to write it here, but the Entscheidungsproblem, the set of valid formulae, maybe I'll just call that V, the set of first order statements that are valid. Those are all here, whereas their complements are all over here. And later on in a subsequent lecture, you will learn that in some sense, these are actually all the same problem. In other words, given an instance of one, you can transform it into an instance of the other, and all these problems are what is known as complete. You'll learn an important vocabulary word about completeness, and that will happen in a later lecture. So let's just recap where we have been in the last few lectures. We've started with what you learned about in the previous lecture about Turing machines, and note that there's sort of a robustness to the definition of Turing machines, that just about anything that you would like to tweak the Turing machine model to get will give you something that's equivalent to Turing machines. And basically, it's also going to give you something that's equivalent to programs. And certainly we're familiar with the notion that there are tons of different programs out there, programming languages, and they're all equivalent. Turing machines are really, in some sense, just another sort of inconvenient programming language, but they have the advantage that they're very simple to work with. We learned about the Church-Turing thesis, and that the real meat of the Church-Turing thesis is just this statement, that no matter what notion of programs you come up with, it's going to be something you can implement on a Turing machine. And an important corollary then is that if something is not computable by a Turing machine, in particular if it's not decidable or if it's not even Turing acceptable, then it's not going to be decidable or acceptable on anything else that you come up with that looks like it ought to be a notion of computation that you can actually implement. This was something that will never be proven, but it's something that is pretty widely accepted in the community at this point, although I must say not universally accepted. We've also given some examples of undecidable problems, and central to this universal Turing machine, which just relies on the very basic notion that you can build a simulator for Turing machines or for any other programming languages using a Turing machine. And this gives us examples of undecidable problems like the halting problem and A sub Tm, and in some sense also underlies the fact that the set of valid formulae is not decidable, and even sort of complicated proofs about other natural problems that people cared about and still care about, like Diaphantine equations. And there are many other examples, and you will learn more about these in later lectures. So that's all for me. I hope you've enjoyed this, and I will be open to hearing from you. If you want to write to me, contact me, you can certainly find me online. For now, bye-bye.